Okay, this is an example of a momentum impulse problem from Physics 1000, Auburn University 2013 summer. So this is a little bit like one of the problems we worked in class. Not exactly, but it's close enough. So what's going on here is we have a ball right here that with some mass m1, which initially has a velocity v1 towards the right. And what's going to happen is this is going to hit a pillow which is up against a wall. It's my lovely pillow drawing here. I'm not an artist, which is pretty obvious here, but it's going to hit the pillow and it's going to come to a stop. And we're given that there's some time interval here, and this is the time between when the ball hits the pillow, sort of right here, and when it comes to a stop. And what we're being asked to find is the force it takes to stop the ball. And on first glance you might go, force? Well, I don't see anything in here about a force. So I'm going to have to solve this with a lot of equations, and you absolutely could. You could determine an acceleration here. We're given masses and initial velocities and final velocities. We don't have any sort of positions, but there are kinematic equations we could find that would give us an acceleration. And then once we had our acceleration, we'd go back to Newton's second law, and we'd plug it in here, and we'd solve for the force. And if this is taking a long time for me to tell you how to do that, it takes a really long time to actually do the problem that way. You can do it, you'd get the right answer, as long as you're careful with your math. But in general, there's a much easier way to solve this problem. Anytime you're given something like this with a momentum, and a change in momentum, and a time interval, the natural way to do that is through the language of impulses. And so I'm going to write down how we've defined impulses. And we've defined it in a couple of ways. It's the change in momentum, which, if you remember, if the mass of whatever we're looking at doesn't change, like in this case, we're going to assume that the ball doesn't lose any little pieces, or there's not a mouse that jumps on the ball and rides it for a while. So the mass of the ball is not going to change, and if that's the case, we can define this change in momentum this way, as just the mass times the change in velocity. So that's sort of the first way we've defined impulse, is the change in momentum, but we've also defined it in sort of the more rigorous way as a force applied over some time interval. And so maybe you can begin to see that I can get at the force from using these impulse considerations without having to go through all the kinematics and Newton's second law and all that stuff. Some problems, kinematics are easier to use. Some problems, Newton's second law is easier to use. This problem would be a pain to do it that way. So we're going to get at the force this way. So what I'm going to do is I'm going to apply both of these definitions that I've developed for the impulse, this one and this one, and see if we can't solve some sort of, or set up some sort of system that we can solve for the force. So anytime you have one thing, the impulse here, that's equal to two things, the change in momentum and the force times the delta t, if you can solve one of those things, you basically are given the other one. It's the old math language, if A equals B and B equals C, then A has to equal C. So anytime you can solve one of these guys, you can sort of get at the other one, no problem. So let's go to our next page and unpack what we're going to do here. So the first thing I'm going to do is I'm going to solve for the change in momentum. And just from the way we've defined this delta thing here, that's going to be the final momentum minus the initial momentum. So first thing we do with anytime we're solving this, is we find see if there are any zeros that we can plug in. And that might be a little bit more obvious if I unpack what's going on here. M1 times V2. I'm just using the M1 because our mass doesn't change, but that comes from over here. M1 times V2. That's going to be our final momentum. And remember, V2 is 0, so this guy gets really easy. That's just 0. And then minus M1 V1. So what I come up with, because my M1 V2 is 0, so my change in momentum is just minus M1 V1. And I know what you're saying. I could hear it through your computer screens. What in the world is that minus sign doing there? Well, if you think about it, that makes sense, because the way the momentum changes is like this. Initially, Let me get a different color here. Initially we had a momentum that was going in this direction. And if we're going to stop that momentum, in effect if we're going to change it to 0, we darn sure better apply an impulse in this direction. So if you're going to call this one here positive, you've got to call this negative. So it doesn't make, it does make sense that the change in momentum is negative, which if you take this one step farther, that's going to mean that our impulse is negative. Let me change back to black. That means our impulse is negative. And all I've done here is I've applied the definition of impulse. We've said that impulse here, and let me get one more color, sorry about that noise. Impulse here is defined as the change in momentum. And I've calculated the change in momentum here. So all I've done here is apply a few definitions. No big deal, but let me rewrite this to make it a little cleaner. I is equal to minus m1 v1. Now I'm going to go back and apply my other definition of I. I've said that I is also equal to F times delta T. So I'm just going to come over here, and if I is equal to minus m1 v1, and also F delta T, I can just write it like this. F times delta T. And so basically I have it here. I think the rest is just some simple algebra. F is going to be equal to minus m1 v1 over delta T. We know all these quantities. I haven't put any numbers in, but we were given m1 and v1, and we were given delta T. And so we have our force. And so, we sort of have this persistent minus sign here. This guy just refuses to go away. But again, it makes some sort of sense. Remember, we're being a little loose with talking about vectors and everything, because we're really only dealing with things in one dimension. But force is a vector, and what we know from vectors is that direction matters. So all that negative sign is saying is that if you have, if you're going to slow this, or if you're going to change the velocity that's going to the right, you're going to have to apply a force to the left. That's all that negative sign is saying. So just like with if you're going to change the momentum that was originally to the right, if you're going to stop that, you've got to apply a force to the left. Or sorry, you've got to apply an impulse to the left. And if you have a velocity going towards the right, and you're going to stop that velocity, you darn sure better apply a force to the left, which is going to yield an acceleration to the left, which is going to slow down your velocity and eventually stop it if that's what's going on in the problem, and it is here. So the negative sign can get a little confusing. Just be aware, remember in physics, typically when you see a negative sign, it means direction. So if you get to this point in the problem and you leave off that negative sign, it's going to be okay, because really what this problem is interested in is the magnitude of the force, which in math we would write like this. Good old absolute value sign, which is going to go here. So, if you get here, I should have crossed that T there. If you get here and you leave off the negative sign, it's not going to be a big deal for most of the problems in this course. But just know that negative sign doesn't just magically disappear. It tells you something about what's physically happening. And it'd be good to have an intuition of that. Okay, hope this helps with your homework. I'll see you in class tomorrow.